Okay, students, welcome to the second and concluding part of Chapter 7's coverage of electron delocalization. After this lecture, you should be able to explain how resonance affects acidity, identify the products of adding HX and X2 to conjugated dienes, and predict which products would be favored under thermodynamic versus kinetic conditions. Predict the products of Diels-Alder reactions with proper stereochemistry shown, and explain why that product and stereochemistry are favored. And please note that we will skip section 7.8. Alright, so I want you to imagine that I ask you this question. Draw the different resonance contributors or resonance structures of sulfate shown here. I'm not going to do that, but I only wish to mention that you should, from our previous lectures, have the knowledge necessary to do that. Here's the real question. Why in the world is sulfate so stable? Of course, the answer is because of all of its resonance structures. That negative charge on this oxygen shown here is not localized to that oxygen, but is in fact delocalized and shared by all three of those resonating oxygens. So, what does this tell us about sulfuric acid, H2SO4? Well, as you'll note, this molecule, sulfate, is the conjugate base of H2SO4. In other words, if you put a proton on sulfate, that is, replace the negative charge on sulfate with a hydrogen, you get to H2SO4. Well, guess what? H2SO4 is one of the 7 strong acids I ask you guys to memorize in general and organic chemistry. It is, in fact, one of the strongest of the strong acids. So this brings us to the $60,000 question. How does electron delocalization or resonance affect a compound's acidity? Well, I hope you can see that the more stable the conjugate base, the stronger the acid. So in other words, if you've got a conjugate base that has lots of stabilization by resonance, chances are the acid from which it came is going to be very strong. And in general, that principle will hold true. The more resonance and the more stabilization we see in our base, the stronger the acid from whence it came. So what are our take-home lessons from this section? The more stable the conjugate base, the more acidic the acid it came from. The better a conjugate base can handle a negative charge, the more stable it is. Resonance helps conjugate bases handle negative charges better. Therefore, more resonance in a conjugate base generally means the acid it came from is more acidic. Now I'm going to show you a slight variation of this mess housed in a new reaction. You see, if I take a conjugated diene like this one and I add HBr to it, I actually end up getting 2 products. This one and this one. How? The answer is in the mechanism. So here is that mechanism. Electrons come out of the alkene, grab this hydrogen. The hydrogen, of course, gets placed on the less substituted carbon to give me the more stable carbocation. Now, if the bromide comes in and forms a bond with this carbon, the product that I get is this one, which is the first product we see up here. However, you should remember that this carbocation intermediate can resonance delocalize. These electrons flip over. It gives me partial carbocation charge at this position. Bromide comes in here, it gives me that as my product. Hence, we end up getting both products as a mixture in this reaction. Now, one thing that I hasten to mention is that this carbon right here is not a primary carbocation. It is not. It is a primary allylic carbocation, which is much more stable. Remember that by resonance, this positive charge right here is actually being shared by 2 carbons. This one and this one. It is resonance delocalized. Hence, this carbocation actually ends up being even more stable than a tertiary carbocation. Let's try adding a halogen to our diene. As expected, when we take a diene and add a halogen such as bromine, we get 2 products, the one to the left and the one to the right. What is the mechanism? Once again, electrons come out and grab a bromine. We need to remember, however, that that bromine forms this bridged bromonium intermediate. Now what can occur here is these electrons can flip over here and open this ring up to give me the resonance stabilized carbocation at this position. If my bromide comes in here and kicks this one open, I get this product, which is the first one. If my bromide comes in there, it gives me this product, which is my second one. Now this brings us to an important point. For reactions that can potentially form 2 different products, like additions to dienes, we can control which product is favored as long as one is a kinetic product and the other is a thermodynamic product. So what does that mean? Let's give you some explanations followed by an example. I'll now define the kinetic product. The kinetic product is the product that forms the fastest. Kinetic products come from the most stable carbocation intermediate. Kinetic products are favored at low temperature, which we call kinetic control. You can pick out the kinetic product by choosing the product that arises from the most stable carbocation intermediate. Now, in contrast, the thermodynamic product is the product that's the most stable final product. Thermodynamic products are favored at high temperature, called thermodynamic control. You can pick out the thermodynamic product by choosing the product that is the most stable final product, regardless of which carbocation intermediate it came from. Remember this: the more carbons there are attached to a double bond, the more stable that double bond is. That's called Zaitsev's rule. So let's apply that back to our previous example. As you'll remember, in this reaction, the addition of HBr to our starting diene gives two products. Which one is the kinetic and which one is the thermodynamic? Let's re-examine the mechanism. The electrons come out and grab the H. The H goes on the less substituted carbon to give me this carbocation, which of course is resonance delocalized with this carbocation. These are both resonance contributors. Now I'm going to stop right here. Before we look at the actual products, I'm going to ask you guys the question: which of these two intermediates is more stable? I've got a secondary allylic carbocation and a primary allylic carbocation. Which one is more stable? It's, of course, the secondary allylic carbocation. Hence, because that is the more stable intermediate, the product that arises from it is the kinetic product. What this really means is that if you are running this reaction at low temperature, like negative 78 degrees Celsius, this is the product that you would get as the major product. The reason is because this more stable intermediate is the one that would be favored at low temperature because it can't go back and forth as quickly or as easily at that temperature. Does that make sense? Kinetic product always arises from the intermediate that's the more stable intermediate. So now let's see if we can figure out which one is the thermodynamic product. Remember that the thermodynamic product is the final product that is the most stable final product, irrespective of which carbocation was more stable. So what we do is we look straight at the products. I've got a product right here. It's a mono-substituted alkene. And I've got a product right here that's a di-substituted alkene. Which of these two alkenes is more stable? Remember Zaitsev's rule. The more substituted the alkene, the more stable the alkene. Hence, this is the more stable final product. At high temperature, basically any temperature that's positive in the Celsius scale, this is the product that will be formed. It is the thermodynamic product. The reason is because at those higher temperatures, this rearrangement between these two resonance structures is happening fast enough that we eventually siphon off all of the product to our thermodynamic product instead of getting a bunch going to kinetic. I hope that makes sense. Now we'll look at some questions. Of the products formed in the following addition reaction, which one is kinetic and which one is thermodynamic? And what is the major product of this reaction?